So, friends, good morning and welcome to this lecture series of geomorphology. Today, we are going to discuss about the wind erosional landforms. So, if you remember our last class, we are talking about this wind erosion. The mechanisms of erosion has been divided into three parts. One is your deflation, then abrasion, then attrition. And to summarize it, we can say by this wind deflation, we are able to create a desert pavement. By wind abrasion, we are creating ventifacts, and these are the faceted pebbles, which if it is of larger size, that can be used to distinguish, to determine the wind velocity, wind direction, and by this change of this wind direction, we can say the change of this landform process of formation of the landform and its position. So, now we are going to discuss about this product of these wind abrasions. The first and foremost product of this wind abrasion is due to the action of wind as well as its particle together, and this forms the most peculiar mushroom shaped pedestral rocks. See, mushroom shaped pedestral rock, if you see here, the basement or the base of this rock, it is more removal, that is more erosion occurred at the basal part. However, as compared to the top part, this material is less removed. This experiment proves that the median height of wind blown sand transport is only about 1 centimeter over sand layer and about 10 centimeter over rock surface. So, if this is so, now the question arises how a system or a erosional surface is produced which is highly eroded up to this much height. So, further experiment says, additional experiment and field observation agree that there should be a zone of maximum abrasion between 10 to 40 centimeter above ground level, with little abrasion occurs above the height of 2 meters. So, that is why all these abraded landforms in this arid region, you will see maximum abrasion occurs here up to 10 to 40 centimeter from the surface, and gradually the degree of erosion, degree of abrasion decreases. That is why we are creating a rock body which is lower part of the basal part is highly eroded as compared to the top part. So, this type of mushroom shaped rock bodies are called pedestral rocks. Then if we continue with this erosion, suppose we have unconsolidated or semi consolidated material and gullies are formed here. Now, we allow this sand laden wind to interact with this gully surface. So, what will happen here? You see, this gullies earlier it was of fluvial origin and it is erosion is added by this wind action. So, that means both side of this gully, the removal of the material will be more as compared to the middle part. For example, if you see here, if we allow the wind to interact here, erosion will more erosion will occur along these gullies, However, in between this material, this segment will remain less eroded as compared to this gully erosion and this gully erosion. So, that minor aeolian abrasion landforms include chutes and flumes that notch low escarpment around playas and other desert plains. So, these are the chutes and flumes, minor erosion is there. They are aligned with locally effective winds and are probably scored by wind-borne sand being swept through small gullies. So, as we are talking about these chutes and these plumes, they are formed by this wind abrasion around these small gullies, and that is why if you take a profile from here to here, it will look like this. So, these areas they are more eroded by wind and this area is relatively low. These are called chute and plume structure of wind erosion. So, if we allow the wind to interact further, removal of material by abrasion, a landform peculiar to this hull of a boat is formed, that is called yard dung. So, yard dung is another product of wind abrasion, which says it is a streamlined protuberance carved out from bedrock or any consolidated or semi consolidated material by dual action of wind abrasion by dust and sand and deflation, by which the material which is abraded is removed by this wind. This loose material is removed, so that only the rock surface is there. So, this is by this way a yard dung is produced. The shape of this yard dung probably originates from these gullies and their interflues at a scarp edge of the deflation basin and evolved towards relatively stable streamlined bodies with width length ratio equal to 1:4. So, that means if we consider its width as compared to its length, this ratio will be 1:4 and this part will be, these are the gullies and this side is the gully and these represents the interflue. And due to this wind action, material is removed from here, by abrasion, and this abraded material which will lie here, that will be removed further by the deflation action. So, that is why this topography, if you see here, it is looking asymmetrical like this. So, this is the upwind direction and this is the downwind direction. So, by appearance, if you see this tapered downwind end considered to be the shape of least resistance of a solid body immersed in a moving liquid, it looks like the hull of a boat. So, this is indicating the wind direction. Here this asymmetrical shape, if you see, this side is downwind direction, this is the upwind direction. So, this is yard dung. So, another type of wind abrasion feature, it is mostly found in Argentina, Andes, and Central Andes, Chile and Bolivia. These are the linear groups, linear gullies that is found in ignimbrite. Why these linear gullies are said to be this wind product or wind abrasion product? You see, the tectonics, the ignimbrite emplacement directions and other factors, they do not satisfy the direction of this alignment. So, that means it is believed that these are the gullies. Earlier it was created by the fluvial action, later this, due to this wind abrasion, this gullies widens and this free space was filled with the sandy material. So, here on the high, cold, arid, dry alpino plateau of the central Andes of Argentina, Chile and Bolivia, wind eroded linear gullies in ignimbrite. So, a consistent northwest southeast orientation for about 18 degrees south to 28 degrees south, independent of local slope, tectonic trends and ignimbrite emplacement directions. So, that is why it is believed these are the groups or the gullies which are formed by this fluvial action first and later it was modified by the wind action. Plateau with the abrasion preferably elongated and extending those open joints that are aligned with the wind and perhaps with drifting sand filling those joints that trend obliquely to the wind directions. So, these are the trends, these are the groups which are formed in the ignimbrite, and these groups are filled with sandy material or the abraded material from these wind directions. Then another type of erosional feature which is called deflation halos. We know deflation, it is the selective removal of finer materials. So, once the finer material is removed, that means it creates desert pavement, but sometimes what happens, this removal of material may be extend to certain depth, so that it reaches about this root level of the associated vegetations. So, form quickly by wind erosion on exposed erodible terrains. When this vegetation on stabilized dunes is destroyed by fire or overgrazing, blowouts develop within months. When excavated below root depth, a blowout can grow as deep as effective wind and can lift the sand. So, now in this figure it can be explained here. We have a block consisting of sand and some vegetation, this is the root level, we allow the wind to pass on it, blow on it. So, after months, if you see, due to removal of this material, we are creating a depression, and the depth of depression reaches up to the root level. So, this is called deflation hollows, and those materials which are removed from here, that will be deposited somewhere here. When we will talk about the classification of dunes, we will talk about this parabolic dune. Mostly those parabolic dunes, they are formed around this type of deflation hollows. So, the limiting depth of blowout is usually the water table, because once the water table is there or above the water table, there will be capillary action, some Vadose zone will be there. So, in that, due to this adhesive force of this water with the sand will remain intact. So, either it will reach up to this water table or up to reach or it will reach close to the water table, that depends upon these conditions of the material. So, the limiting depth of blowout is usually the water table, because most sand resist deflation and plants may grow on the floor of this basin as well. Once we have water table, it will promote vegetation to grow, and water table, this adhesive force between water and sand will increase. So, it will resist further deflation. So, this blowout depth, maximum depth is up to this water table depth. Sometimes the water table is exposed and is forming a isolated pond, that is called oasis. Larger closed basins in arid region, some of them many kilometers in diameter and more than hundreds of meter in depth, have variously been attributed to solution, differential compaction, faulting and deflation. So, as a geologist, we must be cautious about what type of depression we are dealing with. So, in arid region, these are the other possibilities that the deflation hollow can be formed or depression can be formed by solution also, because it is mostly the calcium carbonate sand particles are there. If it is dominant, then solution is the major factor. Then differential compaction, we know we have these sorting differences, there will be somewhere there will be sand, nearby there will be silt. So, those area are more porous, that will settle down fast, and that is why differential compaction occurs. Faulting, in arid region, if there will be faulting through the fault scarp, through the fault plane or the fault zone, there will be depressions and deflation itself also. So, that means by looking at depression in arid region, it should not always come to this mind that it is formed by deflation only. There may be the possibility that other process may work, or this different process may work together to form a hollow. So, irrespective of its, only if this size and depth is more and it is reach up to the water table, then water comes to the surface and it is forms a oasis. But deflation hollows we only and only we use the terminology if the removal of material or depression is formed by deflation only. Big hollows near Laram, Wyoming is about 5 kilometer wide, 15 kilometer long and 100 meter deep. Here this is the Google Earth image of this hollows, and this is a photograph taken away from it. So, it is considered an inactive blowout developed on fine grained Mesozoic sedimentary rocks. Only the water table can limit the depth of deflation if structures do not produce a gravel lag and wind strength is adequate. So, that means you see deflation will continue up to that, either it is the influence of water table is there, otherwise it will covered by a gravel lag, and gravel lag if it is covering, that means we are creating a desert pavement there. So, if gravel lag is there, then further wind action reduces. So, that is why a depressed part here, this is in Wyoming, we are getting a 5 kilometer wide and 15 kilometer length and 100 meter depth hollow is there. This is due to deflation. It is notable that erosional desert landforms or landscapes, unlike fluvial landscapes, do not evolve towards the ultimate base level of the sea. This is very important, because whenever we talk about this fluvial environment, the erosional level, the maximum level or the maximum depth a river can erode, it is the base level. But here there is no question of base level, it is a dynamic process. A sand can be removed from here and sand can again deposited here. So, there is no leveling that up to that depth it can erode, but here we take about this water table depth, this erosion can occur, or the depth where there is a depth at a certain arbitrary depth where there will be a gravel lag, then erosion will stop or relatively reduce there. So, there is no relation with the base level of erosion. Although tectonic desert basins seem to be sediment troughs, it is possible that some basins could deepen almost without limit by deflation alone. Here if you see this extensional basin of this basin and range province, this is an arid zone, wind is actively acting, at the same time it is tectonically very active and it is forming forced and graben structures. And these here tectonics playing major role in modifying the landscape along with this wind action. But here if you see the tectonic desert basins like this type of basin and range province, where these are the sediment troughs, because whatever due to tectonic action, whatever the due to this breakage of the rock, whatever the sediment is produced, it is deposited within these gravens. It is possible that some basins could deepen almost without limit of deflation alone. So, deflation may or may not work there, it is not dependent on deflation, because tectonic is active here, extension is going on here, new and new faults are added here. So, that is why there will be depressions, there will be subsidence. So, here by as it is a tectonically active basin, we should not say it is those depressions that is only occurred by the deflation, but deflation may work there, but this majority of this activity or this basin configuration, basin modification is carried out or it is governed by the tectonic process. So, now let us go to this consolidated sediments. The sediment is horizontally deposited or horizontally deposited sediment. Here landforms in horizontal bedding, cliffs and mesas, bedrock landforms. Cliffs will be there. Here we have cliffs vertically facing slope face. If you remember when we are talking about the slope evolution, mass wasting, cliffs are those which are vertically or near vertical surface of the slope and which is characterized by free fall of this material, only air resistance will be there. And mesa and butte, these are two different terminology here. Bedrock exposed along cliff breaks away along joints. We have different joint surfaces. Suppose we are joint like this, one set of joint is like this, another set of joint is like this. So, through these joints wind action will be there, abrasion will be there. So, gradually it removes this material, abraded material by deflation, and the joints gradually widens with time. So, this side joint is migrating inward, this side joint is migrating inward. When the two sets of joint join together, a part of this rock is isolated here. So, it has certain height, it has certain surface area, it has certain base area. So, that means this will be called mesa or butte depending upon its B by H ratio. B is the base and its height ratio. So, based on this base length and its height, its ratio is defined whether we will assign it the name mesa or butte. Cliffs retreat in flat rocks create plateau. Here cliff retreating creates plateau, these are the plateau surfaces. Then mesas, buttes and finally chimneys. Now, you see mesas where the B by H ratio is greater than 1, butte where B by H ratio is less than 1 and it is less more and more less than 1, then it is called chimney. So, chimney it is simply a linear or it is a columnar form of this rock, it is chimney. For example, here it is a chimney, but if it is base height ratio is more than 1, that is called mesa, and it is less than 1, it is called butte. Then the same type of erosion if it occurs in non horizontal beddings. So, that means here the bedding surface is dipping. So, bedding produces linear ridges, non horizontal bedding it produces linear ridges. Here you see, suppose we have alternate hard and soft rock, this part is soft rock, this is hard rock, again this is soft rock. We allow wind to blow on it. So, due to this soft rock, the first it will erode this part, it is easily eroded and removed, and the hard rock remain resistant. So, that is why you will get a topography of like this. So, this is called cuesta and this is a scarp, this is a resistant layer, it is non resistant layer. So, this is cuesta is a dipping surface, here it is a steep joint controlled cliff, less steep deep slope. Then Inselberg is another part, here if you see here this is Inselberg is eroded remnant of almost complete cliff retreat. If it is less eroded, then it is you see primary bedding structure is there and there is bedding shape is there or bedding form is there. So, here it is called cuesta. We allow it to erode abrade. So, that means gradually its size will reduce and finally, we are getting a reduced form and this is called Inselberg. So, Inselberg is the eroded remnant of almost complete cliff retreat, and Hogback is steeply dipping beds create a symmetric ridge, and cuesta steep joint controlled by cliff, less steep deep slope. So, these are the definitions of these structures. Then pediment, again and again we allow it to remove the material, finally, we are creating pediments. So, pediment we have already discussed in last classes, what is the pediment, how they are formed, what is their significance, how they modify. So, pediment is a very gently sloping 5 to 7 degree sloping inclined bedrock surface. It is typically sloped down from the base of the hill or to the plains of the escarpment, may continue to exist after the mountain has eroded away. So, these are the pediment surfaces. So, with more and more removal of this material, with more and more erosion, this type of cuesta will converted to Inselberg will converted to pediment. Now, depositional landforms of aeolian sand. So far we are discussing about these erosional landforms, that means material was being removed from the system. Either the system was the loose material itself was removing, or the loose material and air jointly they were bombarded on the consolidated rocks and forming they are widening the spaces, widening the joints. So, those are the erosional processes, and from now onward we will discuss about the depositional landforms. So, that means those removed material by the wind, it will be transported and will deposit in a place, that is called deposited materials or the depositional landforms. So, a patch of sand on a desert plain has a curiously definitive size limitations. Under gentle winds barely strong enough to stir the sand grains, the patch is spread downwind and grows thinner and dispersed. So, now suppose as we know we have three types of materials, one is bare rock or hamada, and sandy rock, that is earth, and the rocky surface, that is called, or this pebbly bouldery surface, that is called redge. So, now we allow the wind to blow. So, depending upon the wind speed and depending upon the vegetation, depending upon the availability of the material, those material they change their position and their shape depending upon the wind velocity, direction. So, different shapes they give rise, sometimes it forms dunes, ripples like that. So, that means gentle wind barely strong enough to stir the sand grains. However, if the wind speed increases, these sand grains are picked up and it is spread on the surface, and finally it disappears from that position. And that disappeared sand grains, they may be transported to long distance or short distance, that depends upon the velocity or depends upon the speed of this wind. If no new sand is delivered that place, so from upward wind, because the available sand there is sheltered by bedrock or gravel irregularities. Suppose we are not allowing addition of the sand to that position. So, that means those sand which was available and we allowed the wind to transport it, that will finally spread from their places and it will disappear. But if we allow the wind to add material from the upwind, salted material that is coming up, so that means this surface continuously removing and continuously adding the material. So, that means here this depositional landform will be of different kind. Under strong winds, however, a pre-existing sand patch larger than a critical size of a few meters grows in thickness and in size as its upwind border extends still further upwind. So, that means even if the wind is strong, then the material can remove from this place and material can add this place. So, that is why you will create a depositional landform either in this downwind direction or here. So, depending upon the sand supply. So, when we are talking about this behavior of related to wind transport dynamics, that means here some factors are affecting this wind transport dynamics. One is the wind speed, another is the material available, and on which surface the wind is being blowing. So, because if this wind is blowing on sand surface, its velocity or the speed is absorbed by the sand, and that speed, that wind speed, it is transferred to this movement of the sand and saltating effect starts. But if it is wind is blowing on bare rock surface, that means the wind speed is increasing. So, here if a patch of sand is there and it is being allowed the wind to pass on it, so it will redistribute the sand in the downwind direction, and finally with time this total sand surface will be vanished, but sand is added to it, that means a deposition will take place or so. So, that means it is completely about this changing behavior related to the wind transport dynamics, whether this landform will form or the landform will disappear. So, this is all about this wind transport dynamics. I think we will stop here and we will meet in the next class to discuss about how this wind system dynamics changes the landform from one to another. The shape of this landform, the size of the landform, the position of the landform, how it will changing, we will discuss in the next class. Thank you very much. Thank you again.